A warm welcome to today's webinar, which is organized by the Malaysian Iron and Steel Industry Federation, MISIF, and conducted by the International Molybdenum Association and the Nickel Institute. It covers the topic selecting the right stainless steel. Today's presenter is Dr. Graham Sussex, consultant for the Nickel Institute. I'm your host today, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar. Over to you, Graham.
This is two pictures of uses of stainless steel external. On the left, we've got a handrail, and you can see the differences in the appearance from an electropolished coupling at the corner and the polished, braided railings there. That's something that you deal with after you've actually selected your right material. So that's the processing. And across on the right is simply a picture of a bridge in Newcastle. You can see how close it is to the ocean. They had to assemble it in the factory, and they moved it in on, I think, 3 nights, because there are houses down to the right. You can perhaps see the lights there. Okay, what I'm going to be talking about is why stainless steels resist corrosion, picking out the family that you're going to be using, that is, before you look at the corrosion resistance, and then what's going to affect your choice. And I'm not going to, well, I've written down an order there, but that often isn't the order that people do. But anyway, those 4 factors. What standards don't tell you about your stainless steel, as in when it really doesn't help, for instance, if you're going to be drilling or bending, and estimating corrosion resistance using pitting resistance equivalent, and when that doesn't work. Then I will look at levels of stainless steel you need for particular chlorides and temperature, and also a brief word about pH variations. 2 very brief slides about, might be 3, about stainless steel underground, and then something about crevices and finish and chemicals and electrochemical treatments, but not a lot. That's a whole series of talks in themselves. And then a little bit about the IMOA, and actually ASTA had some input into that too, model for atmospheric service. Okay, why do stainless steels work? Well, unlike ordinary carbon steel, which get wet with chlorides and they rust, and they just keep rusting until they fall apart. If you add 10.5% chromium, and that's the international definition of a stainless steel, then you get a very, very thin passive film on the surface, and that protects it. That's the model that applies to all stainless steels. Excuse me. That's ones where you're relying on a chromium oxide film on the surface to protect them. It's nanometers, as in millionths of a millimeter thick, and it's not strictly an oxide. It starts out as an oxide hydroxide, but it's the same effect, and it will start reforming within milliseconds. This is an illustration of the passive layer, and as you can see, I've written it down as hydroxide oxide, nanometers thick, and it resists corrosion. It doesn't absolutely stop corrosion, but you could say that 10,000 times the rate of reforming of the layer is the amount of corrosion that would occur. So it's, I won't say it's invulnerable, but provided there's oxygen there, it's going to be very good. The 5 families, the ferritics, which are used for sheeting, the austenitics, which are widely used everywhere, the 300 series, the 200 series, which use manganese rather than nickel for forming the microstructure, and the duplex, which is a mixture of the austenitic and ferritic. And interestingly, you mix 2 things together and you normally expect you get the lowest properties, but in fact you get double the strength and lots of corrosion resistance. The martensitics, if you want to go cutting things or making blades, just like the martensitic carbon steels, have high carbon and they get very hard, and unfortunately not a lot of elongation, so they're a bit brittle. And the precipitation hardening, you won't see them unless you're in the aerospace industry. So what's going to affect your choice? Well, availability. 70% of the stainless steel in the world are austenitics, about 25% are ferritics, and about 5% are the others. That's the duplexes, the martensitic, the precipitation hardening. And that's for that reason, most of the stainless steel you see is going to be austenitic. What sort of product sizes do you get? They are not actually the same for stainless steel and carbon steel all the time. A lot of them are the same, but a lot of them are different. There's a generic stock guide on the Stainless Steel Development Association's website, the Australian one. But just be careful in the design. Product form, ferritics will only come in sheet, and they're going to be no more than 4, 5, perhaps 6 millimeters thick, unless you're talking about the utility ones, which are easily weldable and formable and so on, but they only have about 12% of chromium in them. So they're not high level of corrosion resistance. Predicting that is a bit difficult. I mean, yes, alloy content is one of the things, but economies of scale, if you order one sheet, it's going to cost you more per kilogram than if you're ordering 100 sheets or something like that. And then the commercial realities of who's got big stock of it. This is in Japan. This is a ferritic roof, and it's right next door to the bay. It's got about the same corrosion resistance, perhaps a fraction better than 316, and it just runs very nicely. The Japanese have been particularly interested in ferritics, but Europeans have also been going that way recently with design guides and so on. In contrast, this is the racecourse, which is just about to be stopped. It's really near Singapore Airport, so there's deliberately 316 with this 2D finish, a bit less reflective, and 5 millimeters thick. Mainly 5 millimeters, but there's also 1 millimeter thickness as well. So the second thing is, that's availability. What about the properties? Well, the weldability, the toughness, and the ease of forming. And the austenitics win out absolutely hands over. It's because of the way the atoms are arranged. For austenitics, they're on the outside of a little box of atoms that form. And so you get very limited cross-linking, which means it's easy to deform them. The duplexes are nearly as easy, and they have a mixed microstructure. About half is the ferritic and about half is the austenitic. But they have one or two limitations relating to low temperature or very high temperatures. The ferritics in particular have fairly poor weldability. You have to be very careful if you're welding them. Very clean, very good gas control. And also they have limited toughness. If you go down to low temperatures, they get brittle, just like carbon steel does. Magnetic properties are pretty rare as a requirement, but if you are going that way, then the 300 series have low relative permeability, which is basically how they react to magnets, unless you cold work them. So if you bend a piece of 304, then you'll find that it will just slightly be attracted to a magnet around the worst of the bend. There's a frequently asked question on the ASDA website, which is listed there. The 200 series, that's austenitics with manganese rather than nickel, have got relatively low permeability or low relative permeability. And they're used on things like generator slip rings, where you can't afford to have something that's magnetic. And even if you cold work them, they still stay very low relative permeability. And then strength. If the materials have been cold worked, then the duplexes will be strongest, austenitics will be in the middle, and the ferritics will be less. If they are annealed, as in heat treated to get soft, then the duplex will still be the strongest, but then the ferritics are next and austenitics are least. And interestingly, the 200 series are slightly stronger than the 300 series. This is how they fit in strength. And let's look at the really common one, the austenitic, the 300 series. High ductility, as you can see down the bottom, sort of 55%, and sometimes more, of course, and about that level of strength. If you go, If you look at the 200 series, they are slightly less elongation, fractionally more strength. They're not as much used. The ferritic, the 400 series, similar to carbon steel. The forming is similar to carbon steel or galvanized steel. You need to be very careful with welding. I've mentioned that before. And they're used for roll-formed membranes, roofs, and things like that. And note where structural carbon steel sitting just about the same area. And then we go to the duplexes, a lot more strength, about double the yield strength of the austenitics. Good weldability, pretty easy. You still need to do some gas shielding, of course, but they have good ductility, 35% or so against the 55-ish% for the austenitics. And then the martensitics, very high strength, not a lot of ductility, and they're used for fasteners and nodes. You have to heat treat them if you're going to weld them. This is a comparison of the yield strength and the tensile strength of duplexes on the left and superaustenitic on the right. The reason I'm comparing those two is that they both have about the same level of corrosion resistance, but as you can see, there's quite significant differences in elongation and the tensile strengths and the variation in tensile strengths as you go with amounts of cold work. Not really something I'm going to go into in detail. The numbers that I pulled off here come from the graphs on the previous page at the intersections, just showing the effect of cold work on the two of them and how much change it actually makes in terms of the strength and the elongation. Obviously more elongation, less elongation as you've got more cold work. Somebody's asked me a question. Cannot see presentation files documents. I'm sorry, that's not my issue. It's got to be on your computer, I'm afraid. This is looking at relative physical properties, and we're looking at thermal expansion. 304, 316, quite a lot of thermal expansion compared to mild steel, and not very much compared to aluminium. So just basically doing a quick comparison of the 1, 2, 3, 4 stainless steels, mild steel, and then aluminium. Why are these up there? Well, if you're going to be welding, you're going to heat things up. You have to tack them to hold them into position, and you have to hold them in position with various jigs. If you've got limited amounts of allowance for thermal expansion, then you're going to find that the surface will tend to oil can. And there are some classic cases where people have put stuff up in the middle of winter and comes along the summer and the surface goes up and bends, and you just think, oh, well, okay, it'll just contract back. The problem is the reason why it bends is because it's exceeded its yield strength, and so it's deformed, and then got a wavy surface. And the classic example is a court case in England, but I've got lovely pictures of people putting up things in Australia in the bright summer sun, and they wrinkle. This is a very clever design. It's no welding, because imagine trying to weld and then clean the welds up all the way across there. It's two counter directional spirals, Singapore, of course, and it's lots of tension and compression rods. No welding, it's all done up and tightly done there. Very high strength, it's a 2205 duplex. You need the corrosion resistance because of the marine environment. And because people are artistic, they put lights on it, and that's what it looks like at night. If you get to Singapore, go and have a look. It's really worthwhile. And it is worthwhile having a look in the evening too. This is a bridge in Brisbane. It's called the Story Bridge. It's historic. It's heritage listed. And unfortunately, it's high up above the river, and disturbed people have been known to throw themselves off. And so they designed a way that they could put up a barrier. Then they realized that the weight of the things that they were going to put up were too heavy. And so they rethought it, and they designed this arrangement where you've got supports there bending up and over, and they've got black cold drawn 316 stainless steel because it's a moderately aggressive environment. And so from a distance, as in looking at the left, you cannot see the grill. And on the right, it's basically good enough to stop people climbing over. Standards are always going to help, aren't they? Well, not always. If you've got something that you want to drill or machine or bend, then you think, okay, it's been annealed, so therefore the hardness will be a particular number. It can't be more than that. And this is the numbers for 304, 316 and 2205. And we're looking at Rockwells and we're looking at Brunels. Okay, so yeah, but you're not using sheet or plate. You're actually using bar or section. And unfortunately, ASTM A276, there's no maximum specified for 304 or 316. There is a maximum specified for 2205, but they just haven't quite got round to it. And basically, what that means is that you can get yield stress up to maybe 80 or 90% rather than the more normal 30, 40% of the tensile stress. And that can cause real problems if you're trying to drill and you want to use your drills economically. What's the environment? Well, what are the corrodants? What salts are there? And I don't mean just sodium chloride. What gases are there? What fumes and so on? Sulfur dioxide coming off burning coal, or hydrogen sulfide coming from a sewage plant. The physical things, how hot is it going to get? Because if it's going to be above 60 degrees C and you've got austenitic stainless steels, then you might worry if there's chlorides around about cracking. If you're going above sort of 300, 350 degrees C, then you might worry about not using ferritics and not using duplex just because of metallurgical changes that can occur. And what sort of particles are around? Is there sand going to be abrading it? Or if it's in pipes, is there going to be particulate stuff to actually wear? And then what combinations have you got? Dissimilar metals. If you're putting aluminium against stainless steel, will it matter? And that's a complicated function of relative sizes, drainability, etc., etc. And then cycling of stress. Is something going to be suffering from fatigue? Because the austenitics don't have a clearly defined fatigue limit. They basically quote for 10 to the 8th cycle or something like that. What's the humidity? Is it going to be condensing? How hot's it going to get with the sun shining on? And then biological issues. And these are something that it used to be that people would say, oh, it's got to be biological corrosion, because they really didn't want to look at it. But in fact, there are occasions in which it'll happen. In sewage plants, under deposits, not necessarily in sewage plants, there are microbes around which will attack stainless steel. You need special circumstances for it to happen, but you do need to think about it, because there's always going to be spores around that will grow. There's an ISO standard on atmospheric corrosivity in terms of lots and lots of coupons were put out, and they measured what the corrosion rates were in the first year. That's in 9223. AS4312, which is the Australian version of it, slightly different, a little more discerning in tropical environments, because we do have quite a chunk of tropical environments. So we need basically to give you an indication of what materials you might have to use. Then you talk about microenvironments. Okay, so you've got crevices. You've got things that are, well, bolted together and they don't terribly well. Talk about sheltering under eaves, sheltering a tide line. It's not quite sheltering. It's basically the tide comes up to a point, stays there and goes down, or in a tank, you have it at a particular level, and so you can get deposits forming around the water level. And that can be quite a significant corrosion issue. Heat flow, well, the heat goes through, and on the other side, on the side that it comes out into the, say, water, then you can get fouling on the surface. And often fouling is basically going to be the place which the corrosion will occur. And turbulence, and I don't just mean turbulence as in sort of rough flow or bubbling and so on. I mean, you're going down a pipe and you hit a weld and you get turbulence where you roughly double the velocity in the downstream side. Or you go around a sharp curve rather than going around a swept curve and your velocity is high. Stainless steels are very good at resisting that in pipes, much better than carbon steel and much better than copper, for instance. What chemical environment is there? Actually, the straight environment, an acid or an alkali or salts. What contaminants are in it? So you've got metal ions in there that tends to make the thing a bit more aggressive. Concentration gradients. As it is heated up and cooked, you may find out that there are various concentrations. This is more an issue perhaps with wetting and drying, or under the bolt heads, for instance. If it's not sitting down, you get water going in, dries out, next lot of water comes in, bringing more salts, and can be, that sort of crevice can be a problem. And liquid line, I've talked about that briefly before. And startups, well, and closing downs, of course, are the most testing environment because everything isn't stable. This is a graph from AS4312, and there's lots of data there. The bit that I'd like to point out is the red lines across the bottom, because they are a reasonable distance away from the water, but it's a bay. So by the time you've gone more than, well, half a kilometre inland, perhaps even less, you're dropping down to about the background level. Whereas the black squares are an ocean beach, or it's actually a surf beach. And so you go a long way inland, and it's a lot of bouncing up and down because of the variations in deposition. But you've gone, what, 2 and 4.5 kilometres, and you're still not down to the background level that you would expect. The other thing is, what happens with the rain? Now, both of these examples are in Cairns, and both of them have used 304 downpipes. So there's a hot and marine environment. But take a look at the one on the right. Here we've got an elbow, which looks good. Immediately underneath, we've got a polished bit of stainless steel, as in abraded, and then a vertical abraded bit. And you can see that the elbows, both the elbows, are really bright and shiny, despite the fact they're not really well washed. But they were given a very good finish before they came down. Have a look down the vertical pipe, and you'll see up in the area near the top where it doesn't get rain washed and it's quite corroded, whereas down the bottom where the rain gets in and washes it, it looks okay. On the left, we can see the horizontal bit, very sheltered, corroded. Down here and at the bottom, it looks fine. Okay, let's look at the macroscopic things. Marine environments are more aggressive because of the chlorides and industrial pollution from sulfur dioxide or carbon particles landing on the surface. That can be quite aggressive. You've got the carbon to steel potential difference, but you've also got the crevice around. So marine environments are not good. Higher relative humidity near the sea, so it's going to be above the critical relative humidity. That's basically the relative humidity that's high enough to make the salt dissolve. And so you get water films with salt water in them. Sea-generated breezes, yeah, well, they're going to spread the corrodants further. And if you're talking about chlorides, then critical relative humidity is down around 50% or so, whereas with sulfur dioxide, it's up around about 80%. And so you'll have greater times when there's actually moisture on the surface. And that's used as a characterization of surfaces, the time of wetness, TOW. And if you've got cyclic wet and dry circumstances of concentration, then the corrosion rate goes up. That's why a cyclic salt spray test is much more aggressive than a simple constant conditions salt spray test. So how do you actually measure it? There's a thing called a pitting resistance equivalent, and that's given by the percentage of chromium plus 3.3 times the percentage of moly plus a bit of tungsten. That's only apparent for one particular family of alloys. plus 16 times nitrogen. So every now and then people look at it and say, that's great, we put lots and lots of nitrogen in. Unfortunately, you can't get more than 0.5% of nitrogen in, and mostly you're looking at less than 0.1, 0.15, perhaps 0.2%. Whereas chromium can go up to 27 easily, in the mid-30s. Moly, you can't go above about 7, and tungsten isn't going to do very much anyway. If that number comes out at more than 40, then it's called a superalloy, not because of strength, simply because it's at greater than 40 will stand up to seawater. Ambient seawater, I might point out, not hot seawater. And nickel isn't in that. So people who do an analysis and say, no, there's not enough nickel in there, the corrosion resistance is awful. Well, it's not true, because the nickel basically affects the arrangement of atoms. So it looks about the mechanical properties of the thing. Every now and then, I've had people come along and say, oh, look, the PRE on this material it's supposed to be 24, and it's actually 23.5. That's not good enough, is it? Well, unfortunately, it's an empirical thing. There's an error bar on it. It's a curve fitting. And anything less than about 1 change probably isn't going to make much difference. I mean, yes, it is slightly different, but it's not the killer. It can easily be blanketed and masked by what the surface finish is, how corrosive the environment is. This thing was originally worked out for austenitics, but it actually works quite well for ferritics and duplex grades as well. But do remember, it's put together for oxygenated, chloride-rich environments. It doesn't work if you're talking about oil or gas, and it doesn't work if you're talking about high temperatures, where it's simply you want a good film on the surface, good oxide film on the surface. So what sort of range will you get? Well, the superalloys, you've got this is austenitic, duplex, and ferritic, and these are just some examples pulled out of the air. The red ones are the ones that are used commonly. And note that if you're talking about the 12 chrome ones, they don't have any nickel in them. And that's just a structural thing, but they don't, they're not very formable. You can bend them, you can weld them easily. And I'm not saying that each of those is the equivalent across there. Okay, how much chlorides will they stand up to? Because that's what people tend to worry about. And if you're looking at PRE of 18, 200 milligrams per litre, and 304, 304L are the usual ones. If you're talking about 316, 316L, PRE of 23, 24, and 1,000 milligrams per litre. The only state the two states where you may get up to levels where the 304 won't work for water supplies is Western Australia and South Australia. There are a couple of areas in Brisbane where you might have troubles, but if you're going in the outback, then yeah, you need to be careful. If you're talking about duplex, 3,500, and if you're talking about the super austenitics or super duplexes, PRE more than about 42, about 42. They've got to be more than 40. And that would be for really brackish waters or seawater. Note that this is for near neutral pH and ambient temperatures. And ambient, we quote 20, but 20 to 25, something like that. And talking about alkaline or variations in pH, typically people will say, well, between 6 and 8 is about neutral. But if you're pushing it, then you need to think about it a bit. Okay, this is a whole lot of data and plotting PRE across the bottom and critical temperature. This is a test in a solution of either ferric chloride or 3% sodium chloride. It's not environmental conditions, but look at what happens with crevices. You don't get the same amount of high temperature thing for a given alloy. Okay, so 316 is down here. This is a duplex. This is super duplex is going to be up here, and you're going up to really high alloys there. You use stainless steel for appearance. This has got a 200-year design life. Parliament House in Canberra. Been up there, been up, right up to that spot. Beautiful view of Canberra. The surfaces are moderately rough, but the only sort of contamination is the boggon moths coming part. Well, actually, not anymore. There's not nearly as many as there were, but quite a rough finish, about 1 micrometre out. And it's 304 or 321, which is just a version of 304, which is easier to weld. And they're talking about 200-year design life, and yeah, not a problem, the amount of rain that there is up there. I won't make jokes about hot air rising. This is a tower that was built in the 60s, was it? 62 to 65 in St. Louis. And look at the thing. There's no way anyone can maintain it. So it had to be made out of stainless steel rather than painted carbon steel. There's a little tramway inside it and little hatches up there. They went and did a survey of it about 10 years ago, I suppose. And it's got a little bit of corrosion, but most of the problems that they found were welding defects, and they had to tidy them up. Yes, unmaintained. This is Sydney. This is a glass cage, basically. So the idea is you're inside and you're looking out, and you don't want to be looking at lots of things. So imagine that you had the tension structure here was in painted carbon steel. It's not terribly strong, but not very strong. And secondly, anytime it gets scratched, then you have to paint it. So they made it with 2205, smaller diameter things there, and they don't have to do anything other than wash it. And that's pretty easy to do. One of the advantages of duplex. Another one is that you get lots of strength and not a lot of weight. This is in a very remote area where transporting was basically by helicopter, which was not very, well, it had to be done, but yes. High strength to weight ratio and good corrosion resistance. Although the corrosion resistance probably wasn't really needed because it's in the mountains in Scandinavia. And okay, let's get really down to the nitty gritty of it. Here we've got chlorides across the bottom. We've got temperature up the side, and we've got alloys. 304, this is against pitting. Okay, 304, 316, and what you're looking at, 20 degrees C. 304 in theory, on an engineering basis, will cope with 200, 300, 400 parts per million. In practice, the limit that is given is about 200 by the Nickel Institute to give you a bit of margin. About 1,000 for that. 2205, 904L, that's another austenitic, so duplex austenitic, and both duplex and austenitic, the 6 moly and the 2507 duplex. And where's seawater? Seawater is about 20,000 parts per million. So in theory, 904L will work, but you'll see in a minute that it won't work if you've got crevices. If you've got higher pH, so if it's alkaline, all these curves move across to the right. This is the other thing that happens. Here is a piece of 316, which was mistakenly used as a heater tube in some hot phosphoric acid, which is a bit impure. And so it's pitted all over the place. Actually, it's rather interesting looking at a radiograph here. You can see sort of lots of black holes. Okay, across to the left here, we've got an area that was brown, and this is very, very badly pitted. So rough surfaces corrode faster. Over here, we've just overwhelmed it. And note that welds typically are over alloyed, so most of the weld is all right, except for right along the bottom here, where you've got probably a bit of a crevice, and so it's corroded there. This is inside a food factory. People use sauces with lots and lots of chloride. They cook them at high temperatures, neutral sort of pH. This is, the circle there is about 30 millimeters across. You can see the polishing, and they just left it in there for too long. And when I say food sauces, I mean things like tomato sauce. Soy sauce is, of course, a lot worse. So what happens if you've got crevices? Well, all those curves move way across to the left. Okay, so if you're talking about 304, you're down about 150 parts per million chloride at 20 degrees C. Across to the right, there's two graphs, the red one and the black one. And plate heat exchangers, which are quite commonly used, have very tight spacing. They're excellent in terms of heat transfer, but you need to have enough corrosion resistance because otherwise you won't be able to cope with high levels of chlorides. Remember, seawater is up at 20,000, and over here we've got the red sort of in the open, which is the 254, whereas in the tight, really tight crevice in a heat exchanger, you've got to knock back the corrosion resistance. So, as I say, plate heat exchanger have quite severe crevices. All of this is about crevices. So if you go back and look at the other one, I'm not going to do it now, but if you go back and look at the ordinary one, you'll see that all of these things are moved across this way. Equally, if you make things more alkaline, they'll move across to the right again. Sometimes even super duplex doesn't like it. Both of these are examples of using unfilled PTFE, polytetrafluoroethylene, or Teflon if you want a brand name. Very soft, compresses down so you get an extraordinarily tight crevice. Both of these, super duplex, sitting in seawater. The one on the right was there for about 3 months. The one on the left was there for about a year. And very severe corrosion. So you have to choose your alloy, your gaskets, and make sure that they are not making very tight crevices, which means you really don't want to have the gasket material coming out beyond the edge of the flange, because at that point, if you're exposed to the fluid, then you've got a very, very tight crevice, and the tighter the crevice, the worse the corrosion. Other ones, sticky labels aren't too good, crayon markings, biological growth, chemical deposits, perforations. The perforations at coatings, people spraying carbon steel on offshore platform, and some of the coating drifts in the wind and lands on stainless steel, and they wind up with corrosion around the edge of that blob of coating. Or under absorbent coat gaskets, that's just bad news because it stays wet for longer too. This is 304 in seawater, and the seawater was used because it was going to take them 6 weeks to do the hydro test of it, and basically they had to get the thing finished. So they put it in 304 seawater 4 weeks, and they got corrosion quite badly. This little thing on the right, on the left, is basically an area where obviously they bent this thing and pushed in some carbon steel. But most of the corrosion is around where the castellated washer sat down to basically make it stay put. Yeah, not a good design. This is plain rubbish. This is a piece of 316 pipe, Victolic joint. So you basically cut the thing to length, roll a groove into the outside of it so that you're looking at the inside here. There's the roller where it was. And the seal is from the rubber gasket, which pushes onto the end of that and seals to the next one. Nice and easy and light to put in, loved by the building people. The problem was this was used with 316 underground, 7,000 parts per million chloride, oxidizing manganese iron, so it makes it a bit worse. Temperature wasn't too bad. The pH was slightly alkaline, but it wasn't enough. So it perforated through at the edge of the crevice where the end of the gasket was. Okay. The obvious thing is put in super duplex. I hate to say it, but I think what happened was that they put in heavy galvanized and thin. Said, well, it's going to last for 5 years, so it'll be all right. No comment. This is down by the sea. This is Sydney North Beach, and 4 years. So you've got a 304 bolt there, obviously, but you've got crevices there. No maintenance, fairly severe marine, a week from the crevice, 304 bolt I've talked about. The bulk stainless up here, it's electropolished. It's a bit rough, 1.5 micrometer RA, but the electropolishing gives you really quite good corrosion resistance, except where the chlorides can build up in the crevices. And it's nice and vertical, so it drains away, except around the bit. And also, I suspect on the top left, the lower gasket, the lower washer, I think is probably a 304 rather than 316. So let's polish the surface up. This on the left is just an abraded surface. It's massively expanded, of course. That's what the surface looks like if it's done by a machine, so it goes nice and curved. And you're talking about an RA of about 0.2 micrometers. If you electropolish it, you take all the peaks off, and so you get this sort of shape, and an RA which is, well, less than half. And 0.5 micrometer RA is about the break point in terms of good corrosion resistance. All right, we're talking about chlorides. Let's now talk about chlorine gas, because you're trying to sanitize something. For 304, you can cope with about 2 milligrams per litre. You need about 0.5 milligrams per litre, about 0.5 milligrams per litre for good, safe killing of the bugs. And down to about 2, it'll still be reasonable. 316, 5 milligrams per litre. 2205, oh, that must be more. Well, no, actually not, because you're looking at what it actually does to the surface. So the accepted level is about 5. So despite the difference in corrosion resistance there, for chlorides, for chlorine, they're round about the same. There are alloys that will take higher levels, but they're not usually used because they're more expensive. And you don't really need lots and lots of chlorine because you just don't need it to kill the bugs. The other problem with putting lots of chlorine is that you get chlorine vapor coming off, and above potable water reservoirs, you can get corrosion of the stainless steel walls simply because chlorine lands in the condensation on the walls, and you can get rusting. So short-term dosing, 25 to 50 ppm, fine. 24 to 48 hours, not really a problem. You do need to flush it thoroughly. One of the things that you sometimes see in hospitals is people wiping down surfaces with a rag with hypochlorite on it, and then they don't rinse it. And so you wind up with a rust line or a rust scrape across the surface where the chlorine was left. If you're talking about drinking water, it's got to be sterilised. Note that the chlorine is going to react with pollutants. So if you've got water that's got lots of pollutants in it, you have to worry about what's it going to be at the end. And that's why people monitor the level. It will also diffuse away from open surfaces. So if you're looking at a hydrotherapy pool and it's not used for a while, then you'll find that if there's a handrail going down or a vertical pole going down in the area around that pole at the water level, you may well wind up with a bit of corrosion simply because there's too much chlorine in there and the level is immediately above. The chlorine just diffuses out and then drops into condensation. So those limits up here are for minor crevices, for room temperature, sort of 20 to 25, with no oxidizing metal ions. Remember I talked about oxidizing metal ions in the underground, and pH 6 to 8 or something like that. And hey, that fits beautifully for ordinary potable water. If you put lots of chlorine in a piece of stainless steel pipe, you get holes in it. So that was 12% bleach, sodium hypochlorite, sorry, at about pH 13, so it's pretty stable, but it still did that. And this is what happens above. This is a reservoir where you've got chlorine, sort of room temperature, drinking water sort of levels of chloride, and it's just sitting there, condensation on that, and little droplets where the chlorine goes in and then attacks things. This is different. Here's a potable water tank. It's used for storing raw water. And within about 3 months, you had the reputation, you want to have a shower, go and walk around the outside of that. Because the welding was a bit rough as guts, and there's a strong suspicion that the heat tint wasn't cleaned up properly around the welds. It's clearly been strip polished, but not very well. And so you've got all of this. And the reason it goes up and down, it's outside, it gets heated up. So the little chloride, the corrosion product comes out, the ions, they combine with oxygen, precipitate out. And if it's hot outside, then it goes up. If it's cold outside at night time, it goes down. This is what happens in the bottom of the tank. If you've got deposits sitting there and you've got a bit too much chlorine or a bit too much chloride under some sort of deposit there, you've got a bit of attack. And here you've got a weld, which is a really weirdo microstructure, all sort of points. So once it gets started to corrode, it gets going down between the grains and it just sort of creeps down like that. This nice flat rolled structure, not nearly as susceptible. Okay, the other thing is, if you're looking at hot water, as in more than about 60 degrees at neutral, then the austenitics, this is 304316, tend to stress crack if there's reasonable amounts of chloride. There was a rule around 60-60, so 60 degrees C, 60 parts per million chloride, but it's not a good rule. Basically, if you've got significantly above ambient temperature hot water with lots of chloride in it, then you need to be careful about stress corrosion cracking. How do you avoid it? If you've got water dripping on the outside of a hot water tank and it's got chlorides in it, then you can get cracking from the outside. And generally, you try and weld that up and the crack just keeps running away from you. Duplex grades are very resistant and ferritic grades just are immune. And the high nickels are really very resistant, 904L, 25% nickel. You know, these are very resistant, but also a lot more expensive. Duplex grades are the usual things that people use. Surface finish. The smoother it is, the better the corrosion resistance. So mirror polish, bright annealed, that comes from the mill. A 2B, a cold rolled finish, the most common finish around. That's pretty resistant. These are both the same. Well, satin pulp out of a mill or post-mill repolish. And the European version of that is a 2J, but the 2K is the standard. This is ASTM number 4. 2K is similar. 2J is actually tying it down. It says it's got to be better than 0.5 micrometers and a uniform sort of finish, so you don't have crevices of metal sitting there. Rolled finishes, very, very smooth to limit marking, and micro smooth. If let's say you're forming it into a shape like on a roof, it can be very, very smooth, so it won't corrode, but it's going to be macro rough, so you won't get marking. And of course, you can chemically treat it to get more corrosion resistance or electropolish it. And this is just doing a comparison between the European standard and the American standard A480. The Americans don't have a specific specification for 0.5 micrometer. They just say you should be able to get reasonable care, 25 microinches, which is about 0.6 micrometer. Whereas this 2K and the 2K finish absolutely is specified in the European EN 10088.2. And so just polish, yep, that's indoors. If you're going outdoors, get better than 0.5 micrometer. And if it's a 1 in front, this is the American thing, then it's a hot roll. If it's a 2, it's a cold roll. And what happens if you put them into a salt spray test? It's a terrible test for stainless steel. But look, that's what an RA 1 micrometer, 1 micrometer, and look at all the flaps, all the little crevices there. At 0.3 micrometer, a lot smoother. And that's what the corrosion resistance looks like. If you've got a mirror finish or electropolished finishes, so a mirror finish up here and electropolished finish down here, and there's the sea rolling in. This is East Coast, the Pacific rolling into Australia. Hey, both look pretty good and both will stand up fairly well. This will be the electropolish will be marginally better. This is looking at surface roughness versus corrosion resistance. And it's corrosion resistance measured by voltage, but let's not worry about that. Up the top is the best. 360 grit, 220 grit, 220, 80. That's the sort of surface roughness you might get for a 2B surface of a particular thickness. That's 0.5 micrometer. So 2B in theory would be pretty good, but not quite as good as you might want. So there's 220, there's 36. Let's chemically treat them. We have to change the scale because the corrosion resistance is a bit higher. We start off with the 220. It's down around here as ground. If we pickle it, then it's about there, which is about where a 2B would be. And a 2B has the last thing that it's done to it, hot rolled, annealed, and pickled, and then skin passed, but it doesn't make much difference. So that's a pickled level. And that's if it's passivated. And the difference there is that a pickled thing has had hydrofluoric in it, nitrogen hydrofluoric, to clean the surface up, whereas a passivated one started out as a clean metal, and you're basically improving the corrosion resistance on the surface. And then you have maintenance. Goodness don't you do. Over to here, this is the ocean, 50 metres away. These people washing the salt off. And down around here, it's all being washed by the fresh water. It's in Sydney, so it's reasonably good chloride level. Up the top, no, it's just the roughness. And so you can see these areas up here. Maintenance by poster, well, hey, come on. We're looking at what do we do? Don't put too much chloride in, don't make it too hot, and don't leave it for too long. More is not better. So what's the differences between something in air and something in water? I'm sorry, I'm going to run a little bit over time. In air, the corrosion is going to be visible. It's 20% oxygen. There's always going to be oxygen in it. The pollutants will be able to get there. They may be able to accumulate if you've got a sheltered area underneath the eaves or something like that. If they're on a nice vertical surface, it'll wash away. If the corrosion products accumulate, yeah, well, that may protect it, but if they're a bit porous, then the chlorides can get through and cause problems. Temperatures are going to be variable outside, you just don't know. And rough surfaces, remember the 0.5 micrometer, may well trap pollutants. Corrosion underwater, you usually don't see it. I mean, it's down there. Yeah, you might once it's gone on for a while. You have about 8 parts per million of oxygen saturated if you're talking about ambient temperatures, but it doesn't get used up unless it's closed. So if you've got a flowing pipe, then more oxygen will keep coming. I mean, yeah, the flow may be good enough to remove the corrosion product, but usually it doesn't. And the pollutants and temperature in the water can vary. You may have hot water, you may have cold water, you may have raw water, you may have distilled water. And crevices can be a really significant issue because underneath the crevice, you have low oxygen. Outside, you have high oxygen, and so you can drive the difference between those two. What about underground? You can't see it. So you hope that it was put in properly. The water content comes from thin films on soil particles, or it can come from underground streams. Underground streams may not be too bad because they may not have much oxygen in them. Except if you're in Coode Island, silt under Melbourne, yeah, there's oxygenated streams and there's lots of sulphides around, so it's very aggressive. If you're talking about sand that's dry, then, hey, there's oxygen access, but nothing much going to get going on. But you can get all sorts of range between. You can get corrosion products which can accumulate and make things worse, or you can get biological reactions if you've got vegetation rotting down, and you can get microbes causing quite severe corrosion. Temperature's usually stable and often quite low, but if you've got a pipe going through it and the pipe's got warm water in it, then you may need to consider what condition would be on the outside of that pipe. And stray currents from trams or electrical faults, yes, they can be a problem, but not if you've got proper earthing, and hopefully the things are going to be deep enough so you don't get stray current issues. And if you've got a pipeline that's in a trench going across a floodplain, or it's a place where they basically put the drainages in under what was a marsh to build a new factory, then even if you backfill with nice clean sand, you may find that you've got bugs growing and causing corrosion under a pipe. Okay, so let's look at what the difference is between a pipe being put into the ground and a driven pipe. if you're burying something, it's relatively shallow usually, and salts and water and possibly even oxygen can get through. It's unusual for the cover to be adequately compacted. And if you say, oh, no, the spec says, go and have a look at a place where they've dug up a pipe and then put it back in the footpath or along the road, and then look at the road, at the bump from that. So you get diffusion of water, oxygen, and corrodants going down if it's not properly compacted. So let's drive in the pile. It's going in the composition of the soil from the top down through the sand into whatever's there until the pile resistance basically says that's it. That's often going to be below the water table, but even if it isn't, what's going to happen? Unless the substrate's a river, a silt bed like the Coode Island Silt in Melbourne, or the 10,000 metres of sand you've got in Perth, then the end of the pile is in an anaerobic and reasonably non-corrosive condition. Even carbon steel usually only gets micrometers of corrosion. So burial and driven piles are definitely not the same, and driven piles are basically, they survive a lot better. So guidelines. This is a very complicated slide and you won't pick it up immediately, but across the thing, we're talking about maximum chloride concentration. Down the side, we're talking about resistivity. And while that is obviously going to be affected by that, really this column on the left is looking at how much water is there. And if you're talking about putting 2205 into a 15,000 parts per million chloride, then, sorry, resistivity, very high levels of, chloride, yeah, 15,000 parts per million chloride. Whereas 2205, you wouldn't expect to work terribly well. In practice, it will usually work quite well, simply because you've got a barrier all around it of the soil, which basically stops the corrosion products going away. And hey, that means the corrosion stops. Basically, you need good drainage, uniform clean backfill. If you put a pipe down in the ground, you don't backfill it with the stuff that's around it. You use uniform backfill and compacted. And chlorides across the top, but they're measured by leaching the soil. That's the Australian standard, it's the American standard. It's the best estimate you can get. If you're worried about it, if you've got a real problem, then put petrolatum tape, and I've used the word Denso simply because that's the one that's mainly used, but there are lots of them around, with about a 50% overlap, 55% overlap. Very effective. And the Australian practice is to use 316, 316L rather than 304, 304L. The Americans tend to do the 304 because their soils tend to be less chloride than sulfides. And if you're talking about austenitics in this graph here, or this table here, you could equally well use a duplex or a super duplex. This is stainless steel tested, actually it's stainless steel and carbon steel and lead and copper and all sorts of things. Tested for more than 10 years and pulled out. The stainless steels worked very well, except where they were driven in vertically, and you wound up with differential aeration effects down the bottom. But horizontal ones, yeah, you went down and they were better. If you came near the surface, then you got more of a surface thing because these were buried rather than. There is several Nickel Institute publications on the earlier versions. I'm not sure if they've got the 10-year one because it was translated later from Japanese. All this was done in Japan. And so let's assume that you're going to do some testing and you put in your pipe work and then you run out of funding to look at it. And so this is 33.5 years later. This is a burial site. There's all the coupons underneath there. And they were dug up and looked at. But the first thing is, whereabouts is it? And let's remove the trees. Okay, final bit. There is an IMOA ASDA jointly thing. It's on the IMOA website. And you assess the environment, mainly pollution. You assess the amount of salt separately. So you look at where you are in relation to the sea and how much activity there is. It's an onshore wind. Yep, more activity. Rolling surf, even more activity. What's the weather like? how much rain comes, what's the humidity like? And if you're talking about the exposure conditions, is it going to be rain washed? If it's polished, is it polished vertically so it drains, or is it polished horizontally so things get trapped? What sort of chemical treatment was happening? Was it passivated properly chemically? And what was the surface roughness? Is it 1 micrometer RA? Is it 0.5? Is it a mirror polish? And how often is it going to be washed? Maintenance schedule. Mind you, we're not talking about this as the natural washing. We're talking about, is there a maintenance schedule? And it goes into a Excel spreadsheet, and you put in a bit of instruction, the environment, the salt, the weather, the design, and the maintenance. It's an exe file, so people can't send it to you. You have to actually download it. It's quite useful. And section 4, design considerations, you just pick out what you were, and you get a number out of the end. So the the best places is surface finishes, pickled, electropolished, and the roughness is better than 0.3. The worst place, surface roughness, worse than 1 micrometer. And boldly exposed, so it's usually rain washed, or vertical surfaces with vertical grain, both are reasonably neutral in terms of design. So where can you get information? Well, the IMOA, what I've talked about, the World Stainless, ASTM for standards, you can get the standards from Australia, Standards Australia too, or from your local. Sorry, I'm almost wearing an ASDA hat. And the Nickel Institute have got a lot of information. So go and have a look, have a prowl around, put in whatever searching variables you want. And that's about it. My apologies, I've gone 6 minutes over. Any questions?
Thank you very much, Graham. Dear listeners, if you have any question concerning this presentation or about any nickel-related topic, kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner, Technical Help. Click on it, register, it's free of charge, and then fill in your question. One of our experts will come back to you shortest. Thank you all for attending this webinar. We are looking forward to have you on one of our next webinars again. Goodbye.